Hello everyone. So in this video we will discuss about the homogeneous nucleation. So what is solidification? It is a process in which atoms are converted into an ordered solid state from a liquid disordered state. So this diagram will be shown from delta G versus T. So in this pi axis is delta G and x axis is T. So for a liquid to solid conversion for a single phase, G versus T curve will be shown like a single curve like this. So in this, that liquid is unstable below melting temperature and above melting temperature liquid is stable. So the curve is shown at the downside, and in the solid curve it is upside, and below melting temperature solid curve is downside, that is delta G is minimum, and liquid curve is upside, that is delta G is more. So in this video we will see when liquid converts to solid. This is liquid, this is solid. So at the melting point delta G will be 0, and above the melting point delta G is greater than 0, and below the melting point delta G is less than 0. So in this condition delta G is equal to G of solid, that is beta, minus G of liquid, should be less than 0. Then only solidification will happen. So here if we can see, this value is less than 0, so transformation takes place in this range. This value is greater than 0, so no solidification will happen here, and this is the delta G is 0. So below this value, this side, transformation will happen. So what is the nature and mechanism for solidification? So these are randomly, all these kind of particles, these are randomly oriented nucleation of embryo in liquid. So this matrix is considered as a liquid, and these are the particles. So these are the randomly oriented nucleation of embryo in liquid with different directions and angle, which solidifies and gives the polycrystalline material, not a single crystal. So what is nucleation and what is growth? So we can see this is the first stage of nucleation, this is second stage, more number of particles or embryo has been shown in the second stage, and this is the third stage. Here we can see that different grains with the different direction and size are there. So this is the polycrystalline material. Now we will see the definition of what is nucleation. So formation of tiny stable particles of solid beta which can convert into bigger size or which can grow. So those are called the nucleation. And what is growth? So increase in the size of these stable particles is called growth. Like here we can see the particle size is very less, but if this particle will grow, then it can make the bigger grain. Now we will see what is homogeneous. Okay, so we will see here what is homogeneous nucleation. The probability of nucleation occurring at any given site in the volume of parent phase is identical to that any other site, so which is called homogeneous nucleation. And in contrast with the homogeneous nucleation, heterogeneous nucleation is defined the probability of nucleation occurring at preferred sites. So this is the most important difference between homogeneous and heterogeneous nucleation. So here the preferred sites are shown much greater than any other sites. So this is the difference between homogeneous and heterogeneous nucleation. Now we will see practically, like let's take 1 centimeter volume which contains 10 to the power 23 atoms on near about any atom. If the nucleation can take place, that's called homogeneous nucleation. And if 10 to the power 5 atoms nucleated out of 10 to the power 23, then it's heterogeneous nucleation. So for the preferred sites, in case of heterogeneous nucleation, examples are like nucleation at the grain boundary, like nucleation at grain boundaries, or precipitation at grain junction. So these kind of preferred sites are for heterogeneous nucleation. So far we have seen in case of homogeneous nucleation, the nucleation sites can be anywhere in the liquid, in the entire volume of the liquid. But in case of heterogeneous nucleation, the sites of nucleation will be at preferred, like nucleation at grain boundaries or precipitation at the grain junction. Now we will see about kinetics of homogeneous nucleation. So if we consider a particle nucleated in a liquid volume, like this is the liquid entire and this is the particle generated, we are considering a spherical particle. So this is the beta particle and with the radius r. This is the r radius particle nucleated in the liquid volume. So the volume of this beta (4/3 pi r cube), and area will be 4 pi r square. So this is the interface. This is the interface between liquid and beta. So interfacial energy will also contribute in this mechanism of solidification. Now we will see, consider a spherical nucleus of radius r, volume transferred. So what is the exact equation which will make the entire solidification mechanism easy to understand? That is delta F is equal to delta F or delta G. We can take delta G also. Delta G is equal to 4/3 pi r cube, and delta G is the volume transferred. So we are coming from liquid to solid. So delta GB, that is delta G should be less than 0. So it will be like G of beta minus G of liquid. This is solid and this is liquid. So delta G, this is 4/3 pi r cube, delta G B plus 4 pi r square gamma. Gamma is interfacial energy and delta Gv is the percentage volume free energy change. So it will always be positive. Sorry, this is always negative, and the contribution of interfacial energy will always be positive. Okay, now we will see how we can see this volume change in case of solidification from delta G versus R. So this equation of solidification from liquid to solid will be considered from this. So in this curve we will see that this first term contributes to this curve, that is volume free energy, and the second term, which is area into interfacial energy, that will contribute to this curve. And from both these curves we will get this curve which shows the activation barrier and critical embryo, that is radius of the particles which can nucleate. So this is the maximum value which shows the R star and corresponding value of delta G star. This is the interfacial energy curve and this is the volume free energy curve, and both the addition of these curve will give this middle curve, which which is linearly going to the value of R star and then decreasing. So why it is happening, we will see this. So when the value of R is small, that is R square will be more. R is small, then R square will be more than R cube. For larger values of R, R cube will be more than R square when R is large. So why it is happening, we will see mathematically. Like if we are taking the value of R that is small, like R is 0.5, so we will see here that R square is 0.25 and R cube that is 0.125. So mathematically we can see whenever R is small, R square is greater than R cube. And if we will see that the values of R is greater than 1, like we are taking R is equal to 2, then R square is 4 and R cube is 8. So here R cube is more than R square. This is the condition. Okay, so this is the mathematical reason for forming this curve. First, it is increasing to a value that is R is very small, and then it is certainly started decreasing. So first this R square curve is continuously increasing, and after that in the combination with the volume free energy curve, it is continuously started from here, it is decreasing. So this is the combination, this is the middle curve is the combination of two curves, first interfacial energy and then volume free energy. So first the interfacial energy will play a dominant role, and after that the volume free energy will play a dominant role. Okay, let's calculate R star corresponding to delta G star. So we will see from this equation we will calculate the R star. So in this curve at R star the slope is 0, that means delta G star upon delta R equal to 0. This is the condition. Okay, it would be delta G actually. Delta G by delta R is equal to 0. So we will calculate that 0 is equal to 4 by 3 pi 3R square delta G V plus 8 pi R into interfacial energy. So it would be like 4 by 3. Okay, so 3 will cut it out, so it would be only 4 pi R square delta G is equal to minus 8 pi R into interfacial energy, and we'll calculate R star directly, minus 2 interfacial energy upon delta GV. So this R star is this value, and we can calculate delta G star also by putting R star into previous equation. So the previous equation is this one. Here we can put the value of R star here, and we can calculate the delta G star. That will correspond to the delta G star. The delta G star will come out 16 by 3 into pi this gamma q upon delta GV square. So delta GV, how we can define? So delta GV is equal to delta H minus Tm delta S. So at the point of no solidification, the delta GV is equal to 0 if then we can see that delta S is equal to delta H by Tm. So at delta G we can calculate delta H minus delta H upon Tm into T. So it will come out 1 minus T upon Tm into delta H. So delta G is equal to delta H delta T by Tm. So this is delta GV, delta GV equal to delta H delta T by Tm. So we can put this delta GV into R star and delta G star equation. So it would be like R star is equal to 2 sigma by delta GV, which I have been calculated initially. So delta GV is equal to delta H delta T by Tm. So this is minus 2 sigma minus 2 interface energy upon volume free energy change. So delta GV we have calculated already. So this is minus 2 interface energy upon delta H delta T by Tm. So finally this is the relation between undercooling and R star, where undercooling is delta T. This is also called delta T is also called degree of undercooling or supercooling. Which is the major requirement for the homogeneous nucleation. In case of homogeneous nucleation, we need delta T. Without this delta T, the homogeneous nucleation will not proceed easily. Now we will calculate delta G star by putting the value of delta GV into the equation. So delta G star will be 16 pi by 3 interface energy cube divided by delta GV square. That will come out 16 pi by 3 interface energy cube upon delta H square delta T square, and this is multiplied also by the Tm square. So this will be the final equation for delta G star. So we can conclude like this is the important formula for calculations in homogeneous nucleation, that is delta G star is equal to 16 pi by 3 sigma SL cube, that is interface energy, and this is the melting point, and this is the enthalpy, and this is the supercooling part. So about the supercooling, one more fact, that delta T is equal to Tm minus T, where delta T should always positive. So this is the delta G star, this is the delta T supercooling, this is the critical radius, this is the R star. So minus 2 interface energy multiplied by melting point divided by enthalpy and delta T. This is the delta GV equation. This is the delta G star in terms of volume free energy change, and this is the critical radius equation in terms of volume free energy change. So R star is equal to minus 2 interface energy divided by volume free energy change. So these are the 5 equations which are important for calculation in case of homogeneous nucleation. Thank you. So for more clarification, you can refer Reed E. Hill. And if you like our content, please like, share and subscribe. And for any doubts, please type in the comment box and keep following us, watching us. Thank you.